kind of to get back to just kind of like more into the idea of how we can recover a affine property from images. The assumption that we have an image and we have a correspondence, I'll try to recover like information from this. So just kind of one of the things important, we said that the line at the infinity is one of the property in projective geometry. We talk about the idea that lines in kind of usual geometry, they always lie on the kind of in the real kind of world, like finite world, and we don't have really a definition of a line infinity, because in kind of like geometry we don't have really a notion of lines. We usually can say two lines don't intersect, period, in kind of Euclidean geometry. But in projective geometry, we say that parallel line can intersect in infinity. So we have point in infinity. But if we have two parallel lines, like two pairs of parallel lines that each intersect in the infinity, we can actually compute the line that connect these 2 points, and that will determine a line in the infinity. So this is one of the things which is very, very important. So if we say the nice property about like for projective transformation, that lines in infinity can projected into lines in the infinity. And this is one of the things which is kind of like one of the properties we will also try to utilize in kind of recovering the infinity or the projective transformation, and this is the aim of this work. So if we have the line at the infinity is known, so we will know that it's kind of was an intersection, like we know that these kind of like two parallel lines, and it's also possible to compute the aspect ratio of these two lines. If we know that lines intersect in the infinity, we can compute the aspect ratio, part of the property which is preserved in projective transformation. Just to recall, projective transformation, like the kind of general aspect of projective transformation that only preserve collinearity and the ratio, or what we call the cross ratio, which is the ratio of the ratios. This is the two things which is preserved by projective transformation. Now, let us, like for simplicity, let us transfer line from the infinity to its canonical point, which is, this is pretty much the position of the line in infinity. This could be any line which have one in the end, could be in the infinity, but we will try to look into the canonical position. And let be L a finite line. Any line which is finite, which is L1, L2, and L3, will be any line. The only condition we require this line to be in the infinity is that L3 should be different from 0. This is a finite line, sorry. Then what we want to do, we want to transfer this line using our projective transformation. So if we have L1, L2, L3, anyone, which is we apply the projective transformation, and then we will look into this. Now, one thing which is we should also think is that if we have a projective transformation, we have now one transformation will take us from this space pi1. Will take us from space to space pi2, and we can have another transformation H. A prime projection will take us to H3. One of the things which is we know, because this is algebraic space, now we can compute HA, which is pretty much the transformation between space pi1 to space pi2. So this is what we actually call, this is the Affine transformation, because it's preserve the parallel line and the two issues of this ratio. We will know that between these two are preserved. That means the parallel lines here will be, like the collinearity will be preserved. And also we'll know that the cross ratio is preserved. Now, one important thing which is we realize there is a difference between this one and this one and this one. What's really the issue we have? There is something which was preserved between pi1 and pi3, but it's not preserved between pi1 and pi2 or pi2 and pi3, which is the
parallel lines.
Exactly. So this is pretty much, so we go from one space which is kind of skewed more than the other and go back to a space which is a preserved parallelism. So we know what really space that, what transformation that preserve this kind of parallel transformation. So this is only the one which is can preserve parallel, which one is the affine transformation. So one of the things which is from this one to this one is actually an affine transformation. So which is, the affine transformation is a subgroup of the projective transformation. Now, if we have this kind of like aspect, like the one of the things which is common in when we are talking about images and the projective transformation is the notion of vanishing point. We pretty much, the notion of vanishing point quite exists in almost in most of the images, which is normally it appear as the parallel line in the real world intersect in the created image. Intersect, it's not really in the infinity where we're supposed to be, but it intersect in some point which is in the image space, or appear to be intersecting in the image space. In our case, we call this vanishing point, which is supposed to be an intersection in the infinity. This is what we like see in a vanishing point. So it's pretty much appear as part of the transformation, the perspective transformation from 3D to the 2D images. I'm just showing an example, which is we show maybe in two streets in normal, or just we show it in the kind of in a typical kind of a geometry or simplicity. We see kind of cubes and various perspective view of this cube, which is what the vanishing point we get. So we get here one vanishing point, here we two vanishing point, and then the other one we get three vanishing point. This is the possibility when we look into a cube. Exact from which image we look at, which viewpoint. Now, pretty much this is what we will get when we look at some property, which is we will get when kind of like viewing typical image. So if we think about this image, which is the source image, and if we look at the other image in the top, we look into kind of vanishing point. Just kind of this is exactly kind of maybe to try to bridge. In the previous, like the one of the lecture before this, we talk about recovering mathematically the projective transformation. If we have 8 points, which is mean 4 corresponding points, and we know the corresponding between them, we can recover the projection transformation. And now in this kind of like a lecture, we try to see how we can recover this from the images. We don't need, if we have 4 corresponding points in 2 images, we can recover the projection transformation between them. If we have, now in this lecture, we're trying to look at what if we have less data. And real images, not only possible to get kind of like the correspondence, and then the next lecture we'll see about if we get more points, or how many points, or how we get, if we get noisy point. But right now, we will look at the case we have an image, and we have some information in the image. So if we look at this image, we know that we have the lines, and we have 2 vanishing points that kind of easy to observe. One will be U, and one will be P. The basic assumption that these tiles are rectangular or square tiles. So this is why we know that these are lines which in the source image are parallel, and then the projective like images are not. And then what we will get some like the parallel lines will intersect, or the image of the parallel line will intersect, and they will have 2 cases. One will be U, one will be P. We know that these 2 points, U and V, are in the infinity. Now we look the L infinity, which is the line that connects these 2 points, also exist in the infinity. So if we look, it's easy to see that if we have now the L and M, they intersect in a point U, the same thing, which is any 2 lines, we have U cross V, which will give us the line at the infinity. So this is because the line L and if we have 2 lines, we know from the basic algebra that the cross product between them will give us the intersection points. And if we have 2 points, the cross product will give us the equation of the lines that actually connect these 2 points. Now, if we apply the inverse projective part of the transformation, this is what we will get kind of the image after affine transformation. This is what if we only kind of having the inverse of these two, the projective transformation, we get the image after the affine transformation, which is mean the inverse, which is we recover only from these 2 points, which is now what we get. We get an image which is projective transformation. We take only the projectivity part of this. What we will remain with is the affine transformation. You remember in the previous lecture we say we can take an image in a projective transformation and decompose it into sequence of transformation, which is going from the projective part, which is this Q, and then we go to the affine transformation, and then we go into the similarity transformation. This is kind of one of the interpretation of these kind of sequence of transformation. Is that clear? Okay, now which is mean if we take the projectivity part of the transformation, which is mean we take the inverse that we compute only from the 2 infinite points, we will get into like affinely reflected transformation, which is will be the same one of this, which is what we here we maintain parallel lines, but we don't maintain angles. This is one of the things which is we will be able to see. Now, if we take now how we can compute the vanishing point from length ratio. Length ratio, which is mean we can take the ratio of 2 segments, which is in the original image and on the source and the image. So since this floor we know the tiles, we know the ratio between the points marked along these segments. And now if we know this ratio on the image space, so we know it in the real world. If we know it in the image space, we can compute the ratio between these ratios, which is pretty much if we have the points A, B, C, and D are collinear points in an image, and we have their correspondence A, B, C in the real world, which is because we know the tiles and we can know their measures. Then we can compute the distance between AB and the distance between BC, and this is what we call the ratio. The cross ratio is the ratio between ratios. This is what we call the cross ratio. Similarity, we can compute the ratio between A prime, P prime, and C prime. And then we could present this as kind of like this kind of ratio. We can normalize this. Very easy to know, like this is normalize this, which is we'll take one of them will be 1, and then will be, if we put this as kind of like starting, one of them will be as 0, 1, and then the other will be 0, A prime, and the other will be 0, A plus B prime. That's kind of like just simple notation. And then what we will get, now we can use these kind of like 3 points we already get to compute the projectivity. The projectivity part of the transformation, which will be matrix of 2 by 2. And then what we will be able to get, again, we'll be able to get the vanishing point, because we'll get the projective transformation of this. We can take now any 2 lines which are parallel and compute the projective transformation of them, and we'll be able to get the vanishing points. Is that clear? So we saw how to get, if we get the vanishing point, we can recover the projectivity part and remain only with the affine transformation. And now, if we know the ratio, like the length ratio between them, we can recover further information from the image, which is mean if we know the length ratio, we can recover the affine transformation of this part, which is we see like little by little being able to recover the entire image. Just kind of a little bit about the ratio. Here we have, this is just very simple kind of like example how we can use this to, like we have A, B, C. This is, we have two ratio, which is A and B, and then we have A prime, B prime, and C prime. So the ratio between this one and this one is the same as the ratio between this one and this one. And this is, we should get kind of illustrate how we can compute the point in the... Now, what if we have a circular points, which is we have, if we have a point in a circle in the original image, which is what we called conic. Conic is kind of like, is a circle is one of the possible conics. So if we have a image, which is what we saw in the tile, what's the possibilities we can get on the image? The image of this circle, what it could be? It could be ellipse. What it also? If I take an image exact from the top of the tile, what I will get? A circle. If I take kind of a very skewed image from the side, which is, I will be able to get a parabola, which is, and I also will be able to get a hyperparabola in some, like kind of some of the cases, which is an image of the circle will be kind of any other conic possible, which is, this is what we refer to conics, just kind of to refresh your memories. All, if I have a cone, and depends how I cut this cone with plane, this is what I will get. So if I cut it like this is what I will get, circle. If I cut it with an angle, I will get an ellipse. If I cut it, this is, and we assume the cone, continue also to infinity. So if I cut it this way, I will get a parabola, which is, will be this way. And if I cut it this way, I will get a hyperbola, which is this part and some way the other part here. Is that clear? So the image of a conic, which is, could be any of these conic, will also get us any of the other conic. The same if we have in the tile that we kind of like photographing, we have an ellipse, depends in which angle we actually may get a circle or any other a conic. In theory, we could get any other conic. In practice, like in most of the real like world, we get kind of the common case that we get circles to ellipse and the opposite ellipse to circles. It's only when we consider the infinity part where we'll get a parabola and hyperparabola, exactly like the points where the parallel line intersect. If we have a big kind of like circle and we're taking it from the angle, we don't see the kind of the continuation of the angle, which actually see more hyperparabola or parabola, depends on this angle. So if we think about this, and now let us consider kind of like a little bit in the kind of a complex kind of a case. And if we have a complex number I, and it's a complex conjugate, which is pretty much the minus of this is, which is the same like number. So we will, let us call them I and J, which is I and minus, or the conjugate of I. So every circle intersect like the line on the infinity, like in this case, like after the projection transformation, or like. Okay, so these are what we call the absolute points. These points, which is not the projection of these absolute points, will bring us to line in the infinity. This is the one of the things which is we learn in the property of the projective transformation. So this is one of the things which is so. And circular point, which is points in the circle, are fixed under the projective transformation only and if and only if the H is a similarity. Any other projective transformation will take points on the conic or in a circle or in general to kind of like to something which is some point will go into the infinity. But if they are fixed, which is mean this is a similarity transformation, which is similarity encounter only rotation, translation, and scale, uniform scale. This is what we call the similarity transformation. Is that clear? So if we encounter, if this is circular points are fixed under projective transformation H, this is mean that H only is similarity transformation. Any other, like if it's not, then mean H is not, it's kind of like something more complex than similarity. We need to understand similarity is the simplest part of the projective transformation, which is the projective transformation that only encounter or only include rotation and translate and uniform scale, which is mean it's preserve it's preserve angles and preserve parallel lines and preserve ratio of length. So one of the things which is we can actually write these kind of transformation is a very simple like way, which is mean if I have, this is the similarity transformation and this is the point I, which is I will have it there. So I can write S, since we say it's encounter only uniform scale and angle and the translation. This is the only part will not be zero. This part, which is usually kind of like more exist only in the projective transformation, here it's zero, and here as we have the scale is uniform, and the only rotation. This is how we actually this is how we see. This is only a similarity transformation. Now, this is, we can write it as S multiplied by the EI theta, which is EI theta. This is pretty much cosinus I sinus. This is clear? This is, if we write E minus I theta, this is, we can write it cosinus plus I sinus. So this is how we pretty much write. This is, and this is the I, we have it there. This is what we will call equal to the identity matrix, which is mean if I take any kind of like any I, and it will give me another similar kind of like I, it's up to something which is kind of up to scale factor. But this is if we get these kind of like the absolute points I and J, and pretty much apply this transformation. If we remain with the absolute kind of points, which is mean they are fixed, this is mean this is a similarity. Because if it will be...
I was going to ask, the S, E, I, theta, the S is the scale and the E, I, theta is the rotation. Where's the transformation in the second part of the equation?
This is, if we take the scale, practically what we have done, we take S is the matrix, so this is S is not scalar in this case, which is we can actually multiply by this. So if we take S will be kind of like the matrix that will encounter the scale, because this is pretty much, this is scalar value. So if we take this and kind of write it as a vector, and this is will be a matrix that if we multiply S by E, we will get this matrix. So it's confusing because this is not the same as this one. So it's not really, should be used another like a symbol to represent this. So if we get I going to I or something going to I up to scale factor, then this will mean that this is a similarity, because it's mean the absolute points are fixed. Is that clear? So this is how we know, like, this is kind of like a the case which is we will look at. Let us look at like some of the circular points in the, if this is our kind of looking at the general case, which is a circle. Like we know the equation of a circle, which is x squared plus 1 squared equals 0. And now if we look at algebraically at this kind of like circular points are orthogonal like to the Euclidean geometry. So pretty much we can write these points I as this I transform plus I. This is pretty much what we can 1 with any point which is will be 1, 0, and 1 I 0. This is, we can write this point as this case, just kind of like as the real part and the imaginary part. Now, this is the conic dual of the circular point, which is we're looking at this. We from the previous kind of like a lecture, we know that the dual conic of this conic will be I multiplied by G transform plus J multiplied by I transform, which is this is kind of will be the two absolute conic. Now, if we do this kind of multiplication, we'll get to the unit matrix, or plus, which is here, which is will give us 0, which is the point in the infinity. The 0 appear because this point in infinity. And we know that if we take, this is the way we use a transformation, which is in order to the dual transformation, to apply the projective transformation to the dual conic. So if this is kind of like the dual conic, we apply the projective transformation in this way by having the projective transformation transpose of this multiplied by the conic, which is the conic we represented as a matrix. In this case, this is one of the representation of the conic. This is kind of the simple circle. And then what we apply, like multiply again by the transformation, the similarity transformation, this is we will get kind of also the dual conic. What we realize that in this case, what we will get the same representation of the dual conic, because this is similar kind of like similarity transformation. These are the cases which is if we take circular points and apply the similarity, we will get again kind of points in the same or fixed kind of domain. The same with the dual conic. So this is okay. Now, if we look at the Euclidean geometry, usually we use the dot product of their normals to compute the distance between them. So if we have two lines or two vector in this case, L1 and L and M, each one will be kind of like, we can in the projective space and the same in the geometric space, we can think about a point and a vector as the same. Pretty much there is no difference between them. So we know that how to compute the angles between these two lines. In the kind of Euclidean distance, we know how to compute the angle, the cosinus of the angle between two lines. Yes? It's pretty much the dot product of the two lines. So just to refresh your memory, if I have u dot v equal, to u v, so u dot, this is not dot product, just kind of like normal kind of multiplication, v multiplied cosinus, the angle between them. So if we have assume, if this is the vector is normalized, then pretty much we can this multiplication the cosinus of the angle, or we can write it u dot v divided by u v equal to cosinus theta. Now in the projective space, the issue is a little bit complicated, which is we take L1, which is what we will have L1, L2, And if we take this L1 multiplied by L2, L2 multiplied by M, and this is what we will get pretty much. We get here the dot product of these two vectors without L3, M3. Yes? If I take, just kind of like, if we think about the dot product of x, y, and z multiplied by a, b dot, and c, this is x, a plus y, b plus c, z. Now, if I take this out, this is what I will get here. Now, one of the things which is here, what I will get L1 plus L2 multiplied by M1, like L1 square plus L2 square multiplied by M1 square. And this is what this is kind of remind you. What's the length of the vector? If I think about the length of the vector, this without z, without the z, it will be x square plus y square under the root. And if I take the other one, which is will be again, will be in this case, it will be m square will be a square plus b square under the root. I can make this as a common root of both of them, and this will give us x square plus y square divided by a square plus b square. This will be the terminology, which is very similar to what we have seen here. So this is the length of the vector, and this is the length of the vector. This is exactly this one multiplied by this one under the root. We give exactly the same term. What we will get. The issue, which is we ignored the third, which is in this case, if the third one is 0, what does this mean? We ignore it because it's 0. If we ignore it as being 0, which is what does this mean? This means that the point in the infinity. So this is one in projective geometry. Now we can pretty much either ignore it, like in typical like Euclidean geometry, we ignore it because it doesn't exist. We don't take it into account for vectors in the 2D space. And projective transformation, this is if we take points which is R0, this is pretty much give us that we took the Euclidean space, but in the intersection of the z equals 0. This is what we have done on the Euclidean space. Now, if we get the angle to be kind of here in a projective geometry, it's the angle will take into account, it will be very similar. This is the point M, and this is the point L. Now, one of the things which will be able to get, if these 2 points, now we want kind of to look at what we realize that this is kind of what we assume, we're taking the distance between, this is the dual conic, which is one of the things I think this is very important to kind of get this part first to understand which conic we are doing. This is, we're taking the conic, which is the undefined, the projective plan, and this is only the things which is we can use kind of to measure the Euclidean angle between them. So if we take this kind of the dual conic, which is represented of these kind of like of these points, and now we can compute the angle very simple. And now, if L and M are orthogonal lines, what do you mean orthogonal lines? That means if we take M and N, they should be, if they are orthogonal, which is mean if we are taking the dual conic and multiply both of them, they should be kind of 0. This is why the assumption that they are orthogonal lines. Now, if we remember that we talk about the points on the conic, and the dual conic is actually the dual representation. The dual conic of the conic is represented by all the lines, which is kind of tangent to the conics. This is what we kind of like represent. We represent a point. The dual point is a line. The dual of a point is a line, and the dual of a conics, every point in these lines will be kind of represented as the line with tangent to the conic at this point. Is that clear? It's just, I think it's not really kind of like, sometimes these symbols kind of like give the intuition that this is complicated, but it's not. This is a matrix 3 by 3. This is how we represent the dual conic, the same we represent the conic as a matrix. So pretty much what we will have here, we'll have a vector 3 by 3, which is represented by this line, multiplied by the matrix 3 by 3, and again multiplied by the matrix, which is we get multiplied this. So we'll get pretty much, in this case, this is what we will get. And this will get one scalar, because eventually what we will get, matrix by line, and then again matrix by line, and this is will give us this number. And again, the same is here. We multiplied m by with the dual like a conic, but from one side we multiplied by m, and the other side we multiplied by m transpose, because if this is a column, this is a row, should be a column or the opposite. And this is what we actually doing here. Again, this will give us one number, and this will give us one number. And this is just, I think if you look in the previous slides and look into the conic representation. And now if they are orthogonal, this is mean, one of the things, if they are orthogonal lines, which is mean the dot product of them will be orthogonal. And if they are, the dot product of them will be, they are orthogonal, what the dot product of them will be? 0. And this is one of the things which is we use here, like there is a very kind of parallel notation from the multiplied by the conic and the dot product. We see this is very much along this, how this is represented in the Euclidean space as a dot product, and how it's represented in the kind of the projective space as multiplication by the dual conic. So one of the, if we look at the, sorry. So if we look at the length ratio, so if we look at these kind of like two triangles and try kind of to think about how the ratio between them, and so we have the ABC 3 points, and then we have ABC prime 3 points, and if we take the correspondence between them, then we talk about like the M prime and N prime and L prime is the 3 lines. So if we can, we know the mapping between, if we have the projective transformation that map A to A prime and C to C prime and B to B prime, then we can compute the line L prime, N prime, M prime. This is very easy, because if we have L prime is A prime cross product of P prime, and the same N prime is P prime cross product with the C prime, and the same with the M. So this is one of the things which is, but in geometric space, we know from the, like that this is the angle, we know that the distance, the ratio between this distance, the distance between B and C, and the distance between A and C is the same as the ratio between sinus alpha and sinus beta. This is from the sinus theory. So, and this is what actually will translate the ratio of angles to the ratio of length and vice versa. So if we take this thing, we can pretty much compute the ratio of angles. Now we know how to compute the ratio in on both the Euclidean space and the projection space. So just a little bit, we show how to compare these angles. So if we have these angles, the ratio between angles, it's actually correspondence to this ratio between the length. So we can use either of them. Is that clear? Okay. Okay. And now let us kind of like go back to some of these again, which is these are like, it's look kind of like scary term, but let us really look at this very simple. It's not really complicated, because what we mean here, we mean like in the previous class we say that this is the similarity transformation, this is the affine transformation, and this is the projective transformation. This is pretty much all of these together, we can call them H, the general representation of the projective transformation. And this is exactly the same one with the transpose. So if we say, if we take a dual, like a dual conic, and apply a projective transformation, this is what we will get. Like again, a kind of like a dual conic, or like a representation of another dual conic. And this is what we can do. We pretty much can represent it by taking the H similarity out. And this is what we will remain with the affine and the projective transformation. And the same thing with the other side. Now, if we look at these two cases, just write them as kind of like, which is what we will, the dual conic multiplied by the similarity, and similarity, it again will give us a dual conic, because what we said, the dual conic, if we apply similarity transformation, all the points will be fixed. And now what we will get, we will apply like this dual conic, which is, if we apply this with the projective transformation and the projective transformation, this is what we will get, the general representation. Now, if we think about this, is like very interesting results, because if we think about what we have here, we have V as a vector, which is, in this case, will be kind of vector in the 2D projective space, and K will be a matrix. And when a matrix will be 3 by 3. And this is how we will get, all this will be kind of the general, kind of a 2 by 2, sorry. And this is how we will get the general matrix of the projective transformation, 3 by 3. Now, this is what we, the dual conic, like enable kind of determine the affine component of the projective transformation. So this is why the affine component, remember, what's the affine component of this will be, if you like, what was the affine component? The affine component, pretty much what we get if we go back. Where we saw this? No. No, we still, okay. So if we think about, this is the affine transformation, so what we will get, this part, which is, you remember this part, which is, will be, have S sinus, cosinus, S sinus, cosinus, and this is will be the translation. So what we have, will be the translation part. This will be kind of like this translation with the rotation and scale. This part will give us the similarity. This is in the similarity is 1. The affine will be kind of like this part. This is if we take this part with this as being general vector, this is what will give us the affine transformation out from the projection transformation. So this is what kind of like what we will be able to get by what we call rectifying homography, which is we can recover from actually the dual conic. If we take this transformation and use single value decomposition, which is a way to kind of like decompose the transformation into 3 representation, usually the SVD give us kind of like 1 diagonal matrix and U transpose. And this is what we know, that this is what we will get from this transformation. if we take this as, will be, if we take this as the kind of very canonical dual conic, this transformation, we know that H and U transpose, this is what will give us the projective transformation. Because this is kind of the canonical dual conic, because of the 0 here, and this is 1, 0 of the projective transformation. So if we take this, because we assume this, you remember, will be the transformation of the dual conic. This is what we get. If we manage to take this transformation and decompose it into 3 matrices, which will be, will be the diagonal matrix, will be U and U transpose. We know this is the canonical dual conic. And if this is the canonical dual conic, we will know that this H, T, UT, and U is exactly the H, T, and T we have them in the beginning. Is that clear, or something is a...
H equals U down the bottom, that H is the combination of the projective and the affine homomorphies from the...
Yes. So what we started to say, if we have a projective, if we have a dual conic, and we apply the projective transformation, and eventually we get this result, which is what we see, what we observe is this is the dual conic. So if this is the dual conic, what we observe, we can actually look at this as a combination of 3 matrices, or multiplication of the 3 matrices. If we think about this as the multiplication of 3 matrices, we will kind of think about this as, if we use the single value decomposition to take this matrix and decompose it into 3 matrices, what we will get 1 diagonal matrix in the middle. This is the SVD will give us, and another 2 matrices, which is U transpose and U. And then if we get this kind of composition, we know that this is correspondence to the projective transformation. This is just just kind of thinking about this part as the projective transformation. So if we now take about all this kind of, which is, we try to play with the conics, because in the image we see now the conics. Now if we want to kind of do the metric rectification, which is we want to return back from the projective transformation back into the original image, which is pretty much what we expect, what we want to get here. So if we have L and M 2 lines in the word plan, and we will have L prime and M prime, the correspondence lines to these 2 lines. So assume we have 2 lines, and we want now to recover the affine rectification of the image, which is we assume this image is already kind of returned back to only include affine transformation. Now we want to recover from this one to go back to the original image. Now, what we know from the previous one, since these 2 lines, we know that they are perpendicular. We assume, because we know in the original the correspondence to perpendicular lines in the original image. Why? Because we know these are tiles, and these are kind of lines in this tile. So this is we know this from the fact and the real world. If we know if these are orthogonal lines, this is what we can know, that these lines will be correspondence, if we multiply them by the dual conic, what we will get 0, because they are orthogonal. Exactly the same what we will get the dot product of the 2 lines in the Euclidean space. Now, if we take V to be 0 in this matrix, this is what we will get. If we take V to be 0, then this will be 0, this will be 0, this is the part which we will get. Now, if we take this line and multiplied by this line, then we will get 0. Now, the only thing which is we need to recover in order to take this is that this should be T. Sorry, this is not. So is the symmetric with 3 independent component because we have 2 degrees of freedom in this case. And then what we will be able to compute L1, L2, and this is matrix because all the other parts which will be 0, which is mean that this is why would eliminate L3. And this is we need to solve this equation. Pretty much this is the solution. Now, why we take V to equal 0 in this case? Why this is the general kind of like conic representation. And this is, we know for fact that the transformation from here to here, you need to understand we have already done some kind of like coming back from the projective space. So we get kind of like the translation and the rotation, we take it out from this. So we say it doesn't exist. This is why we actually can assume that these 2 vectors are 0. From the previous slides, we show that this decomposition of the three matrices. I'm trying to see which one we have this. I think the one before this, if I'm not really. Yes. This is the one which is show this transformation. If you recall, we say that any projective transformation, we can represent it as 3 matrices, which will be the projective part, the affine part, and the similarity part. So this is what represents the projective only, because we know in this image we have already rectified the projection part, which means that this will be 0. This is why we take these 2 parts V to equal 0. Now, why we take this instead of 1 to be equal 0? Because we also now, this is the kind of, we use the dual conic for this representation. And this is what we will call that, this is what we want to recover, only the similarity part, which is mean we recover this. Now we are dealing with this. So what we want to compute the K. And this will be able to give us this transformation. No, this is, sorry. Come on. I don't know what I opened here. Sorry. Okay, so this is why we want only this part is 0 and this part is 0. This part is 1, but part is 1 only if we take 0 as 0, 0, 1. If we take this part as 0, 0, 1 and multiply, this is what we will get 1. Yes? But we assumed V0 because this is exactly because we want to eliminate this. This is why we take only the K multiplied by K transpose. And if we take the 2 lines, it will be able to recover the part of this transformation, which is we'll be able to recover the similarity up to scale factor. Up to scale factor. Is that clear? So this is what we actually learned from the conic representation. Here's another example, which is we also can use if we know this information. So we know kind of these correspondence between points. We can take this image. If we know that these windows are rectangular window, we can actually, this is enough to take this image from this state to this state only by knowing these 2 lines. it's not only two lines. We have enough information to do that because we know these two lines and we know that they are orthogonal. So we can, from this, pretty much recover the dual conic representation, which pretty much gives us the information we need in order to do the recover of the entire transformation. So we compute the projective transformation, then we apply the projective transformation to each pixel, each point in this image, and we'll get this image. So this is I think last time we get to also go over this. If you have any question or things which are not clear, like please kind of like drop by and kind of like tell me what things which is. Sometimes maybe I assume things are clear and they are not, so please just kind of like let me know what things I need to go in detail, or if I need to add example, just kind of to know that we are not really missing things. So the next lecture I'll talk about kind of recovering the kind of more the 2D transformation from the if we know the correspondence between images, like points. Okay, if I'm having two images and I have points which is from one image and their correspondence point in the another image, how we can compute or how we can recover the projective transformation. Now, if we have 4 points and 4 points and they are exact, we can use one of these techniques to do these things. And next time just we'll go over this kind of very simple mathematics. But this is not the problem. Usually this is not the case. The case usually we have 2 images and we have many points which corresponds to many points, more than 4. Why more than 4? Because we don't know which are the kind of the most reliable 4, because usually when we capture the image or when we compute the correspondence, we encounter some noise. Now, we don't know which one is the correct point. So we want now to which will give us the best approximation of the projective transformation. So we don't know the exact because we don't know the correct correspondence. And this is usually the case in kind of like image processing, that either because the acquisition was not encounter some noise, or computing the correspondence, because usually you compute the correspondence by computing feature point from the 2 images and then say these points correspond to these points, and they may encounter some noise and error. This is what we will talk in the next lecture. One of the things which is very important to understand is that in the dual space we have the duality between lines and points, in the conic and the dual conic. And it's not really complicated. If you look into this, it's very simple algebra. It's just kind of because I think some people really when they see a lot of symbolics and kind of within metrics kind of think it should correspond to something complicated. In practice, it is not. If you look at the first the first 3 lectures, or the most kind of the third or the 4th lectures, you will see that the representation is very, very simple. Pretty much we are talking about matrices which is either 3 by 3 or 4 by 4. Not complicated than this. The only thing you need kind of to understand that we mainly used cross product kind of to represent the intersection of a line, or to represent the line which is connect 2 points. So pretty much it's not complicated, but sometimes when we look into the algebraic representation, it looks scary, and it's also, we need also to recall what's really the representation of each symbol, not really to think that this is something term which is more complicated than we imagine. So and if you have a question, please come and ask me. So I'll stop here, and then we will I will start from the recovering transformation. And again, if you have a question just in the beginning of the lecture, please ask me, and because in I think 2 maybe next after 3 or 4 lectures, we'll start only reading papers. Okay?